And this is the example we are going to do today. So I will show you how to do a three-dimensional model of a soil. Then if we have time, probably we will add the superstructure, otherwise we will do it in future webinars. But the main focus here is how to do solid modeling, solid mesh. Sorry, I think we have a message here. Okay. Yeah, follow this message, because if someone has problems to hear me, follow these steps here. You can log out and log on with join with computer audio. Yeah, same for you, Valentina. You have to log out and re-enter, selecting join with computer audio. Because I see many of you do not have the microphone or speaker turned on. Okay, so we go ahead, and in any case, you will see the webinar registration if you have a problem or if you missed the first minutes. So, so I will explain how to do this kind of model. So we have our soil profile here, and we want to simulate the fact that the soil is infinite. Of course, we cannot model it. And so to avoid wave reflections, we are going to use the so-called absorbing boundaries. Now, this can be achieved in OpenSees using a mix of zero-length element to simulate Leismer-Kuhlemeyer dashpots and free-field columns. Now, in many examples that you can find online, these examples are restricted to the 2D case, and in this webinar, we are going to explain how to do it in the three-dimensional case. So you will learn it how to do this kind of model, how to do a solid modeling, a solid structured mesh. Then you will learn how to use interaction to define equal dot constraints for the free-field columns, how to create Leismer-Kuhlemeyer dashpots. You will see that STKO has many features to create automatically distributed boundary condition instead of a one-by-one lumped Springer dashboard. And then you will see how to do staged analysis. So we first create some part of the models, and then during the analysis we will add other parts. And finally, we'll explain you how to use the concept of initial state analysis. We will see some problems that this kind of feature has and how to solve it. Okay, so let me explain you all the files that you will find tomorrow on the website, so you can repeat all the things that we are going to do today. So tomorrow you will have two Excel spreadsheets, one with all the material parameters that you are going to use for the soil, for the bedrock, then all the coefficients that we need. And then you have another Excel spreadsheet with the input motion that we're going to use. For the sake of simplicity, we're going to use a Ricker wavelet. So here we have all the equation to apply this kind of time series. And then you have all the files. So we have a 2D drawing to start the modeling. It is just the profile of the soil in 2D. And then from this, we're going to construct a 3D model. And then you will have the three kinds of models that we are going to do in this webinar. The first one is the very basic one where everything is modeled in a single stage. Then you will find another example where we use the concept of initial state analysis. So in order not to have the displacement of the first gravity analysis step, in this case you will see that there are problems of undecided vibration due to mixing the initial state analysis with following a transient analysis. And in the final one, you will see how to solve this problem. Okay, now for the sake of simplicity in this webinar, I will never run an analysis because I already have all the analysis already run. So I will explain you how to do it. And then you can run the analysis. It will take more or less 10 minutes for each analysis. Okay, so let me start from the beginning. And as usual, let's move to the preprocessor. So the first thing that you can do here is to import the 2D drawing of our CAD profile here, of our soil. So it is already in the XZ plane. It's a very simple model. We are going to use this very simple soil profile. We have a slope here. Then I have all this bunch of lines just to make sure that the mesh can be structured. So as you can see, all these lines form quadrangular regions. Here we have some more of them because these 4 regions here will be used later on to place the superstructure. If we cannot do in this example, we will do it in a future webinar. And then these other 2 drawings here are for the free field columns. Okay, so let's assume you have your 2D model drawn like this. If you have seen previous webinar on STKO, you know how to do this kind of 2D modeling. Now we want to turn this one into a solid model. So the first step, when you have a CAD drawing made of just lines, you can create faces out of these polylines just by using the planar command. This planar command basically creates a series of faces starting from a 2D sketch like this one. So I click on planar, I select all of them, right click, and then I have, as you can see, all the faces filling all these holes here. Now the source lines are already selected. I don't need it anymore, so I can just remove them by pressing cancel. And as you can see now, I just have these 3 planar faces. Okay, actually this one is just one face, as you can see from the icon here. These one are called shells. In CAD, shell means multiple surfaces. So multiple surfaces connected by edges, common edges. So at this point, you have this 2D version of our line drawing. Now we need to extrude it to create the 3D model. So you can either use the extrude command, or if you know all the steps of the extrusions, you can do it in an easier way. So of course, the extrusion command is pretty easy. You click extrusion, you select everything, and then you start moving it around. This is not convenient now because we need to extrude it multiple times, and we know the dimensions. So let me first draw a line. And the first thing that we want to do is to do a first extrusion for the first layer of the free field column. It is 10 units. In this case, we are modeling in meters and kilonewtons. So I write 10 in this direction, as you can see. Then we have another 10 meters of spacing. The spacing between the free field and the soil model does not play a role in the model. It's just a space that we use to distinguish between the two parts. So we use other 10 meters. Okay, and then we have 30 meters of soil here, divided in the first 15 meters. Then we have 4 steps at 1 meter each one. I need them just because when I will put the superstructure, I need this subdivision. Then once again, another 13 meters. Then another 10 for the spacing. And the last 10 meters for the last free field column. Okay. Okay, now I have my profile for the extrusion, but actually here I don't want to put anything, so I want to remove this piece of line here and this piece of line here. So how do I do it? If I click on this line, as you can see, I select the entire line. This is because if you look up here, I have selected the button that says select the entire geometry. Now, of course, if you want to select only some sub-parts of this geometry, you can either do it from the work tree. For example, I can expand the node associated to this geometry, and then I go on edges and I can select them one by one, as you can see. Or I can do it from the graphical window. I can just switch off this button here. So I'm saying STKO that I don't want to select the entire geometry, but I want to select the sub-geometries like this. For example, I want to select this one, and then I press cancel to remove them. So as you can see now I have 3 lines, or actually 2 lines and 1 polyline from the center. Perfect. Now I can come back to the entire geometry selection. And now I can use a command which is called sweep. Sweep is pretty much like extrude, but instead of extruding like in a freehand way, I can extrude it following a path, so a sweep path. So I click on sweep, and STKO says, okay, select the profile shapes. The profile shapes are basically, in this case, the faces that I want to extrude. So I want to extrude this, and this. Right click, and then, okay, now select the spine shapes. Spine is the extrusion profile. So first I want to extrude it along this spine, right click. And as you can see now, each faces has created a series of solid. Now, for the sake of simplicity, STKO leaves the selection, keeps the selection of the previous, keeps the previous selection, because now I can either remove it or I can reuse it. Now, in this case, I want to reuse it because I need these faces to do the next extrusion. So I can just click on move, and then I move from this point to this point, the previous faces, so that I can select them once again. And I can click on sweep. And as you can see now, okay, select the spine for the next extrusion, and I select this one. Okay, as I did before, I keep the selection and I move it to the next extrusion path, which is this one. And still, sweep, select the profiles, right click, and select the spine. Right click, and we are fine. Now we can remove the selected faces because we don't need them anymore. Perfect. So now we have all these solids. These three lines are not needed anymore, so I can select them from here, select, 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 and press cancel. Fine. Now we are left with all these solids. Well, some of them, as I showed you for the faces, some of them are simple solids, as you can see from this icon. In fact, they have only one solid. Some of them with this other symbol are called composite solid, like for the shell. So there are multiple solids connected by common faces. As you can see, there are many solids inside this volume here. Okay, so now the entire geometry is ready. Actually, we need to do just one more step. I want to create a hole here, a 4x4 unit hole that will be the place for placing my, my foundation, then the superstructure. And I will proceed as I did before for the polyline here when I wanted to remove these two pieces. So I can go, as you can see now, I will select the entire geometry. But if I switch off this one, I can select any subpart. It can be a faces, it can be an edge or a vertex. Now in this case, I want to remove only solids. So I can switch them off. And I keep only the solid icon. So I can select only solids. And I will select the first layer of them. Okay. Once I have them selected, I just press cancel, and it creates a hole here, as you can see. Well, this one will be the place where we're going to put our superstructure in the next example. Now, for the sake of this example, it is sufficient because we just need some, let's say, some sort of imperfection to make the wave reflect in such a way that we see the effect of the absorbing boundaries. Okay, now we can go back to the full selection. So the first step of the analysis of the modeling here is to create a solid model, and this is fine. So we are done with it. We can just save the analysis. We can just save the model. I will save it in a different folder, so I will not work on the previous one. Let's call it example. And this one will be the model basic, model 3D basic. Okay. So typically, as I've said in many webinars, the mesh is the last thing that you do in your analysis. But when you're doing complex solid modeling, probably it is better to check that your model is good enough to do a good mesh, because sometimes you can do some mistakes in modeling, and so your mesh cannot be generated. So just to make sure of it, you go in mesh. And in this case, for example, I want to mesh everything with a structured mesh made of hexahedra. So I want to make sure that all the geometries I made are fine for hexahedral meshing. So how do I do it? The first thing is to go on mesh controls. Then I go in solids, and I want them all to be structured mesh with odd and hexa elements. Linear interpolation, we don't want to use quadratic elements in this case. So I select all the solids, and I press assign. Done. And then I will use, let's see, let me put a global seed of uniform by size, and I want to put 0.8 meters each one. I will show you later on the 0.8, but as you know, there are limits on the mesh size in this kind of examples. And here in the material parameters, we have the calculation. Our mesh size should be maximum mesh size should be 0.8. So we're going to use 0.8 as a typical mesh size. So I assign it. As you can see now, this is a preview of the mesh size, and I press done. Okay. Now, if I do my mesh, I can check it if it is feasible for it to be okay. As you can see, the mesh has been done, and everything is meshed as a structured hexahedron meshes. We need to do a small modification. As you know, all these boundary elements here are just free fields, so we don't need to do this discretization. So for example, let's say this dimension is fine for the mesh as an overall size. But along these edges, for example, along this edge here, I just want one element because this one anyway is going to be a free field column, so I don't need the subdivision inside. So how can I do it? Well, first of all, let me go in the top view, and then I go in mesh. And as you can see, before I used global seed. Global seed is the typical mesh size in the entire model. But then if I want to change the seed or the mesh size on particular features of the model, I can use the edge seed. Okay? Now for each edge seed, I don't want to use the global setting, but I want to use something different. I want to use the setting uniform by division, and I want to use just one division on all these edges. All these edges here. Same thing in this direction and in this direction. I press assign and then done. Then I run the mesher again. Okay, now as you can see, this mesh here has been done properly. Well, in this case, we use very elongated element because we don't need many elements inside the subdivision because this is going to be a free field column. Perfect. So the mesh is fine. We have checked that our model is fine for this kind of meshing, so we can go back in geometry and keep on working on our geometry here. So let me save this file. Now the next step is to create the so-called interactions. In fact, as you can see here, we have many geometries and they are disjoint. We need something to define how they interact with each other. In particular, we need to create some interaction for the free field columns because we are going to use equal dot constraint to make them act like a shear column. And then we need other interaction to create the Leismer-Coulomb boundaries between them. Okay, so when you're done with geometries, you go to the next step, which is interaction. You can either create them from here, or you can go here on the toolbar on interaction, and you can work here. I personally prefer working on the work tree. So if you want to create a new interaction, you just go here, you click add, you decide a name. Now, in the first stage, we are going to create the interaction for the free field columns along for the free field columns and the equal dot, EDOF, along the x direction. This is a name, so you can use whatever name you prefer. Then you have the interaction type. I said it in many other webinars. We have three options. The first one is the node-to-node links, and here there is an explanation. Basically, you select a master geometry, then a slave geometry, and this option will generate many node-to-node, two-node links. And this is the kind of interaction type that you will use 90% of the cases. Then there are a few other cases few other types that can be used, which is node-to-element or general link, but they are very specific to other kind of OpenSees elements. Now, in this example, we are always going to use node-to-node links. Okay. So when you're done with the settings, you press OK, and STKO says, OK, now select the master geometries. Okay, now in this case, since I want to do the equal dot for the free field, I have to select some faces here as master and other faces here as slaves. Okay, so for the sake of simplicity, I can go on the top view. Since I need to select only faces, I can switch off these buttons here and I leave only the select faces. And then I select the exterior faces. Now keep in mind I'm doing the interaction for the equal DOF in the X direction. So I select all these faces here as masters and all these faces here as masters, as you can see. Okay, right click. And then I have to select slave faces. So once again, I go in top view and I select this one and these faces here. Okay, now this is my selection, as you can see. Right click to accept the selection. And now, as you can see here, basically STKO created, for example, if you want to visualize what's going on inside the volume, I can switch off the visualization of faces. And as you can see, STKO has created many node-to-node links along these sides. Okay, it has a particular algorithm that basically couples the nearest slave to the closest master. That's why I created them in just in one shot here. And now I can do the same in the other direction, because this one was the interaction for the free field equal DOF along the X direction. Now I need to do the same along the Y direction. So I proceed in the same way. Add interaction free field E DOF Y, node to node link. Okay. Once again, I move on the top view and I keep only the face selection, so I do not accidentally select other entities. And then I select the exterior faces here and here as master. Right click. As you can see, we have only those faces selected. And now I have to select the slave geometries. So I select the interior faces of the free fields here and here. When I'm done, right click to accept the selection. And also in this case, as you can see, if I switch off the visualization of faces, I have this other selection, I have this other interaction here. Okay? So all these points, all these lines connecting the corresponding faces along the Y direction. Perfect. So now we have all the interaction needed to assign the equal DOF constraint. Now we need other interactions, because as I said, we're going to create Leismer-Pullemeyer boundaries, and these boundaries will go between soil and lateral free fields, and between lateral free fields and corner free fields. So the first interaction we're going to do, we can call it interaction soil free field for the Leismer-Pullemeyer along the X direction. Okay, so I typically use this nomenclature here. So S stands for soil, FF stands for free field, LK for Leismer-Pullemeyer, and X, of course, for the X direction. So press OK, and move once again on the top view. And as usual, I keep only the face selection. And I want to select the, I'm doing it now on the X direction. So I select the free field columns as masters. Okay, so I have all the interior faces here. Right click so that I can select now the slaves. And I select the faces of the soil, of the interior soil domain as slaves. Now that I have the selection, I right click so to accept the selection. And as you can see here, we created this last interaction here that connects the free field face to the interior soil domain. Now we're going to do the same for the Y direction. So add interaction soil free field Leismer-Pullemeyer Y. Okay, and as we did before, we select only faces. We start with the master faces from the free field columns. Right click, and then we select the slaves faces in the interior soil domain. We have our selection. Right click to accept the selection, and we have also this other interaction here. Now, basically, this one is what you typically do in a 2D analysis. So you connect this soil domain with the lateral free fields in one direction and in the other. Now, of course, if you look at the lateral soil, at the lateral free field column, this one by itself is like another 2D problem. So this one is like the interior soil domain now, and these two are its free field columns. So we need to create interactions between the lateral free field columns and their corners along the x and y direction as well. So we need other two interactions. So here, let's call it interaction free field for Leismer-Kuhlemeyer along the x direction. Once again, I move on the top view. I select only faces. I want to create the connection along the x direction, so I select as masters the faces of these corners. I think I already selected them. Let me see. And okay, it's just a line. Okay, fine. And then also these two faces here as masters, as you can see. Then right click. Now I need to select the slates. And for the slates, I select the faces of the lateral free fields. Like this. And I can right click. Perfect. Now I have this connection here that will be used, this one, to create Leismer-Kuhlemeyer connections, dashpots between the free field columns and the corner free field columns. Okay. Same thing in the y direction. So once again, I go in interaction, free field, Leismer-Kuhlemeyer y. Okay. Master faces. So I keep only faces selection. Let's select these faces and the same thing above. Okay. Right click. And then I can select the slates. And I select this one, and these two faces here from the lateral free fields. Right click, and I'm done also with it. So basically now we have all the interaction that we need. Then you may ask, okay, but I need also free fields on the bottom. We will see later on. There is another way to create actually not free field, sorry, Leismer-Kuhlemeyer dashpots on the bottom. And I will show you later on using boundary conditions. So at the moment, we have all the geometries that we need and all the interactions. Now we can proceed with the material modeling. Okay. So for the sake of simplicity, in this webinar, we are just going to use linear elastic materials. We're going to do linear analysis. The focus here is how to do the modeling and how to create this boundary condition in, let's say, an automatic way. In future webinars, we will start from this model and we'll start treating the nonlinear examples and how to put a structure on it. So let me save it. Okay, next step, we can go on physical properties. The first property that I want to create is, before creating it, let me move on the property tab. So as you can see, when I move on the property tab here, I see everything when there is like transparent. It means there is no property assigned to them. Okay. So the first thing we're going to do a linear elastic material, 3D material for the soil. So let's call it material soil. And as I said, in this first example, we are not going to use the initial state analysis. So we are just simply creating a three-dimensional solid. Then in the next example, I will show you how to use the initial state analysis. So we go under material ND, other ND material, and elastic isotropic. And the material properties can be found here. For the first layer, we use this Young modulus and Poisson ratio. So let me go back here. And we have (2.54). Yes. 2.5 to the power of 6 for yes. and 0.22 of Poisson ratio, 0.25, sorry. And then we have a mass density, yes. Let me see the mass density here. Is 1.6. Okay. And we are going to assign this material model basically to both the interior soil and the boundaries. I've seen in many examples, many 2D examples, that people use to give an increased thickness to the free fields. But actually, in this example, it makes no difference. So we use the same material model. There is no need to increase the stiffness of the free fields, as you will see. So I want to select everything but the interactions. So I want to select all the solids. So I switch off, as you can see here, the selection of the interactions. I select all the solids, and I drag and drop my material. Okay. So as you can see now, they get the color of this physical property here. Okay. Now we need an element formulation for this as well. So when I try to change the color from physical property to element property, once again you see it is transparent. It means no element property has been assigned yet. So we do the same thing. We go in element. Now here, for the sake of simplicity and to speed up the calculation, we use the single point integration solid. So we go under brick, and we use the SSP brick. Okay. Then here we are going to put the self-weight. Let me check the parameter here. Self-weight is 15.696. So minus 15.696. SSP brick, okay, that's fine. So once again, I can select all the solids. But I want to show you another feature, which is, for example, now imagine you have many materials here. So it is not so easy to go and select the same materials you have selected before. You can go in physical property, right click and select. So you can reuse the selection you used for the previous material assignment. And then you can click on the element property and you can drag and drop it. Okay. So now you have both the solid material and the solid element. Okay. So now the next step is to assign something to the Leismer-Kuhlemeyer conditions. Okay. So let's go in physical properties. Now, the Leismer-Kuhlemeyer condition, as you know, in OpenSees, they can be assigned using zero-length elements. So for a zero-length element, we need to create some zero-length materials. A zero-length material is just a collection of uniaxial materials in different directions. Okay, so we first need to create some uniaxial materials, and then we join them in a single zero-length material. So the first thing, we need to create a material for, let's say, Leismer-Kuhlemeyer for the sides along the x and y local direction, so in the shear plane, basically. We go under material, uniaxial, other uniaxial material, and we need the viscous. Okay, the viscous one. Now we use alpha equal to 1, and the C parameter for the Leismer-Kuhlemeyer condition needs to be calculated. I will show you some references. In this case, I was using the description that you can find in the FLAC solver here, and they explain it quite well how to use free field boundaries together with absorbing boundaries. Here you have some theory about it. So if you're interested, you can go in the, let me see, 1.5, 1.4.1. Yeah, that explains the concept of quite, they call it quite boundaries, but they are the absorbing boundaries using the free field columns and Leismer-Kuhlemeyer conditions. Okay, and here those are the properties for the P and shear wave velocities. Now in our case, let me go to the material properties. The shear wave velocity and the, we have one question. Name of this reference, I can post it here, is the FLAC user manual. I will post the link here. Just a second. I will post the link here, and you can go in chapter 1.4.1. 1.4.13, sorry, 1.4.13, quiet boundaries. The explanation is given only for the 2D case, but the extension to the 3D case is pretty straightforward, as I said. Okay, so I will not waste time on the theory. You can find everything here. Let me go back to the material parameters. Okay, so here we calculated the shear velocity and the tangential and normal velocities here. There are function of the bulk modulus and the shear modulus and the density. And here we have the C coefficients of that we need to assign to the viscous boundaries. That basically, once again, are a function of shear velocity and the density. So for the here, the first line, we have those of the soil layer, and then we have the ones of the bedrock, because we are going to simulate the fact that under the soil we have a bedrock with different material parameters. So here we need, for the X and Y, we need the 400 coefficient. So let's write 400, and this will be used for the two tangential directions. And we press OK. And now we need another one. Let me clone it. And we call it LX, Lesmer-Kuhlemeyer sides along the Z direction, which will be the normal instead this time. So for the normal, the coefficient is 692.82. 692.82. The alpha is still 1. Okay. Now that we have these two uniaxial materials, we need to join them together in the so-called zero-length material. So Lesmer-Kuhlemeyer zero-length material for the sides. Okay, I go to model, special purpose, zero-length material, zero-length. Now we have to choose the dimension. In this case, it's 3D. Then the model type. As you can see, we have U or UR. In this case, we are just using displacement element. We don't have any rotation because we don't have beams, so the U is fine. And we want to provide a uniaxial material for each and every direction. So the first one will be XY, the second one XY because they are the same in X and Y. The third one will be the normal one. So we choose LKZ. Perfect. Okay, now we can take this one and assign it to all these connections. But then we have a problem. As you know very well, in OpenSees, the zero-length element does not have a physical geometry. So by default, its orientation is the same as the global axis. And as you can see, the global z-axis is pointing upward, while instead we want the z-axis to point along the line. This is not done automatically, but in STKO, we have a way to assign local orientation to zero lengths. If you want to see the default local axis, you can switch on this button here, and you will see a series of triadrans here, showing the X, Y, and Z axis given by default. As you can see, by default on the interaction, they follow the global local axis. So this is not what we want in this case. Now we want all the local axis of this interaction to have the Z direction pointing along the line of construction. How do we do this? Here we have the local axis. So what I can do, for example, now is to create two local axes, one for all the zero lengths pointing along the X direction, and then another local axis for all the zero length pointing along the Y direction. So for the first step, I need to create one that points the Z axis along the global Y. So I can click on local axis, and I call it local axis C equal to X. It is a rectangular local axis. I press OK. And then it says, OK, select the first point, the origin of the local axis. Now, the origin of a rectangular local axis is not important, so I usually place it outside the model boundary here. Of course, if you choose cylindrical or spherical local axis, of course, the origin plays a role. Now, since I want to put the z-axis according to the x global, it's easier for me to use the left view, okay? So I just click in any point here. First point, second point, and third point to define a plane. And as you can see now, I have a local axis whose z direction is pointing along the global x direction. So now I can select all the interactions pointing along x. So those between the side free field and the soil, and the corner free field and the side free field. And I simply drag and drop this local axis here. Now, as you can see, their local axis has changed, and now the z local axis points along the construction line. So now we're going to do the same for the other directions. Now in the other direction, I need to point the z-axis along the y, so it's easier if I place myself in the front view, like this, and I create another local axis. You can call it LA z equal to y, rectangular local axis, and once again I choose the center, then first and second point. Okay, now I select all the interaction pointing along the y direction. As you can see, this was the default one, and now I drag and drop this local axis here, and now as you can see, the local orientation has changed. So perfect. Now basically all the zero length element here have the same kind of local axis, so they all points their local z directions as the outward normal vector from the faces. Why we did this? Because in this case we can just use the same material model for everyone. Otherwise we needed to create two material models. Okay. So now I just want to select all of them, both those connecting the soil and the lateral free field, and those connecting the lateral free fields and the corner free fields. They share the same material model for the Lesmer-Kuhlemaier because I assigned the same material model in every component, of course. Now, you know very well that if I have different soil layers with different material models, I need to create different Lesmer-Kuhlemaier conditions. So I can drag and drop this. And of course, I don't need to see local axis anymore, so I can switch them off. Now, as I go in color by element property, you can see that basically we have a material model for the zero length, but we don't have an element. So we do as we did before. We need to create a zero length element. So let's call it element zero length. And this is pretty easy. We go in zero length elements, zero length. So this is like the one that you find in OpenSees. We have just one extra feature. Now let me first say that I'm using a 3D model. Then of course you have this option, do Rayleigh, which you know very well is already available in OpenSees. And then you have this extra option, which is called distributed. This one is not available in OpenSees. Why? Because this one is an automation that we have in STKO. As you know, the zero length element in OpenSees is just kind of it's like a spring, a node-to-node link. So if you want to do this kind of boundary by hand, you need to provide a dashpot connecting every node of the master slave faces. And for every zero length, you need to provide an equivalent area. So you need to do the lumping by hand. This means basically that every node-to-node link potentially has a different value. And this one is very inconvenient. But in this case, if we use the distributed option here, STKO will automatically take the values that you assigned in the material model, in this case as values per unit area, because you assigned this zero length between two faces. And STKO will automatically compute the tributary area for each node-to-node link, and will convert the material model into an equivalent one, taking into account this tributary area. So this is very convenient to do distributed condition like this. So don't forget to use the distributed option. So you press OK, and then I select them all once again. and I drag and drop the element. Okay, so we can save the model. So now we have our entire model, all the interactions, we have the physical properties and the element properties. Now we can go on with boundary conditions. Now before doing the boundary condition, we need two definitions, because when we will define the loads, then we will need the time series. So since we are going to do two analyses, I need both a constant time series, and you will see later on why I need it. So time series constant, and this is fine. And then we need another time series for the applied motion. So let's call it Richter wavelet. And in this case, when you have a custom time series, of course, you can use the path time series, where we are going to provide some points here from the Excel. You can go on the second Excel file, which is the Richter wavelet. Here we decided to use Richter wavelet as an acceleration, but as you will see, we cannot apply an acceleration when we use Leismer-Coulomb on the boundaries, so we need to apply it as a force. So we first integrate it to obtain the velocity history, and then from the velocity we can compute the equivalent stress that we have to apply as a pressure. And also these steps are described here. Let me see where it is. It is somewhere here. No, up with this one. Okay. So they explain when you use the quiet boundary, you cannot use acceleration. You need to provide equivalent forces. Okay. So let me use. Oh, I have a question. Yeah, of course, we are recording this webinar. The webinar will be by tomorrow, both on our website, if you go on training, e-learning, and then it will be on YouTube. And not only you will not only have the recording, you will also have all the input files we are doing now. Okay, so don't try to do it now. I mean, you will have everything done tomorrow. Okay, so all the support file, all the Excel files, and the STKO models. Okay, so as I said, we cannot apply an acceleration where Leismer-Coulomb condition are used. We need to apply a traction. So we first use this one as an acceleration, then we integrate it and we obtain the velocity. And it is this one. So in this case, we are going to take the velocity here. You can copy paste it, Control C. Then you go here, Control V, and that's fine. Now you need to provide here a time step. In this case, it was 0.0005. Let me check it. Yes. Also for the time step, you have some limits. If you want the theory, probably you have already seen it in some OpenSees examples. You have limit on the mesh size and on the time on the time step that you need. Okay, so you can go here and look at the references. Now in this case, we choose 5 to the minus 4 as time step. And this is our the time series that we are going to use at the bottom. Okay, then we are going to scale it. I will show you why. So this one basically is the velocity that is going to give us an acceleration, a Richter wavelet, where the top, let me go back to the top, where the maximum acceleration is just 1, is normalized. Then we are going to scale it. Okay, so now we have our definitions. Now we can start creating boundary conditions. So let's first save this file. Now we go in condition. Now the first thing that we need are 3 boundary conditions for the fixities. Okay, so first we need a fix along the x direction. And before pressing OK, we choose the model constraint, single point constraint, fix. We are in 3D, only displacements. And we want to fix the x direction. So we go on the top view, and we want to fix all the vertical faces normal to the x direction. Then later on, you will see how to remove these constraints and to replace them with equivalent forces obtained from the reactions. But I will show you later on. So for the first gravity analysis, we need to fix them. So all the faces pointing along the x direction, and press OK. So we have this boundary condition here. Now we do the same for the y direction. Fix y, constraint, single point, fix 3D y. And then I select all the faces pointing along the y direction. Okay. And the same thing for the z direction. So I go on the front view, it's easier in this case. Fix z model, constraint, single point, fix 3D, and I pick the z direction, and I select all the faces at the bottom level. Okay. Okay, and then we have also the fix here. Now that we have all these conditions, we need something else. Let me see here. Okay, now the next condition is a kinematic condition for the free field. As I said before, this in OpenSees there is not an element for a shear column in the sense that can only displace in a shear. But we can obtain it using a solid element like this and then an equal dot constraint. Basically, you assign a periodic condition between one side and the other so that they will displace in every direction of the same amount, and in the sense that it cannot stretch or it cannot rotate. So we go, as you remember, we created many free field equal dot condition in x and y, and we are going to use them to create the interaction. So we go in condition, add, and we call it eDoff for the free fields. Now this time we go under constraint, multi-point constraint, and we choose equal doff. We are in 3D, only displacement, and we want to make it periodic in x and y, and we want to make it periodic also in the z direction so that it does not rotate. Okay, so we select all of them, and we need to select these two interactions. So the interaction for the equal doff in y and the interaction for the equal doff in x. Okay, so we have all these interactions, then we can press OK. Perfect. So now we assign also this equal doff condition to the interaction for the equal doff. Next condition is the Leismer-Kuhlemeyer at the boundaries. As you can see now, we have two ways of defining Leismer-Kuhlemeyers. The one that I showed, the one that I shown before. We have a question here on the chat. Because I'm going to apply also, because otherwise the first analysis will be static. If I don't fix it, it will be singular, so I need to fix it. Okay. As you can see, the Leismer-Kuhlemeyer condition will be applied in a second stage of the analysis, but in the first stage, I will do a static analysis with a gravity load. So if I don't fix it in x and y direction, it will be singular. Okay. Okay, so as you can see now, I'm creating all the conditions that I need, but then you will see in the analysis step that I will apply them one by one, so not them all at once. Okay. So first we define all the fixities, then the equal doff for the free field columns. Next step is to create the Leismer-Kuhlemeyer for the bottom. Now in the previous step, I've shown you how to create Leismer-Kuhlemeyer conditions between two existing phases. But in this case, we did it creating an element, actually, an element with a material. But what happened when I want to create Leismer-Kuhlemeyer on a phase and the bedrock, which is not modeled, which basically there should be some fixed nodes? Well, in this case, we have another automatism that makes it even easier to create less Merkel-Meyer condition. So we can apply it exactly as a boundary condition, not as an element. So you will see now, I go in add, and let's call it Leismer-Kuhlemeyer bedrock, because in this case, we simulate a bedrock under the soil at the bottom. And in this case, we go under constraints, multi-point constraint, and we have distributed Leismer-Kuhlemeyer in 2D or in 3D. Now we are in 3D, so we use this one. As you can see also, in this case, this element is not available in OpenSees, but STKO is doing this one as an automation, basically. You input the coefficient in X, in Y, and in Z, and then behind the scenes, STKO creates a duplicate of the nodes you select for the boundary conditions at the same position, and then creates a series of dashpots between those nodes that will be fixed and the ones of the selected phases, okay? So it's just a way to create in a fast way a series of dashboards. So in this case, all the alpha coefficients will be 1. Once again, X and Y will be the local direction of the phases that we're going to select. So in this case, we need to select the coefficient related to the shear, but in this case of bedrock. So is this value here, 1920. So 1920 here and 1920 here. While in this case, Z direction is pointing normal to the surface, so it will use the C coefficient for the normal wave, which is 3325.538. 3385 5.8. Let me go and see. I already forgot. 3325.538. 538 and 1 here. Okay, this is fine. Now, since it is a condition, before pressing OK, I need to select all the phases this condition will act on. And this condition will act on all the bottom phases, both of the soil and the free feed columns. So I can go on the front view, and I can select, I can drag and drop a rubber band selection like this, so that all phases are selected, and I press OK. And so we also have this other boundary condition. As I said before, we are just defining them, but we are not yet applying them in the analysis steps. You will see later on. So now we have this condition here for the Leismer-Kuhlemeyer at the bottom. Then what else do we need? Now we need some load. Of course, the vertical load has been already defined in the elements as body forces. Then we need to define the horizontal load, which is actually as a surface pressure, surface traction at the bottom phases that will be used to apply the Richter wavelet using the a force instead of an acceleration. So let's call it dynamic force. Since we have to apply it on phases, we can use a phase force. So we go in loads, force, and we choose phase force. Phase force basically allows you to assign a vector. And this vector, since it is a phase force, should be understood as a force per unit area. Now in this case, we use just one. Then I will show you how to multiply this value with another coefficient. So this one will be just a unitary, a unit phase force applied to all the phases at the bottom. We have a question here, just a second. Okay. Can you offer a downloadable link for this webinar, which you can provide us with a recorded movie of this? Yeah, we are just recording it. So by tomorrow, you can go in, I will show you. You can go in Ask the Soft. Then you go on the support and training. Then you have e-learning. Okay, now let me copy paste this one. Under e-learning, you can find all the previous e-learning, like these ones, for example, where you have all the contents and files, and then a link on the video on YouTube, okay? So you will find both the recording of this one, plus all the support files and STKO files that we are doing today, okay? Of course, they will be available tomorrow. Okay, so, okay, I just assigned the dynamic force, and remember I assign it as a unit force. Then the last boundary condition will be the forces from reaction. As I said before, for the first gravity analysis, we are using some fixities. But then we want, before doing the dynamic analysis, we will remove those fixities, otherwise the boundary conditions, the absorbing boundary condition will not work. So we will remove them, and we will use an automation that we have in STKO to replace those constraints with the reaction forces that we have at that point of the analysis. But to do this, we need to define this boundary condition, which is called force from reaction. So we can call it force from reaction. We go under load because actually it is a load of force type, and you go here and you find force from reaction. And you can specify which component you want to convert from reaction to forces. Now in this case, we want to convert all the direct components. We don't want to convert the moments because we don't have any. So we select only these 3 points here, and then we need to select all the phases where we apply the fixity in X, Y, and Z. So basically they are all the bottom phases and all the vertical phases. So I go here, vertical phases in X, and vertical phases in Y. As you can see, in this case, move always from left to right, because otherwise if you move from right to left, you will select also the intersecting phases. So left to right. So as you can see now, I selected everything but the vertical phases, okay? Everything but the top phases. So I selected the horizontal phases at the bottom and all the vertical phases from the free fields, from the corners, and from the soil. And I press OK. So now this condition will act over all the vertical and bottom surfaces. So now we are done with the definition of the boundary conditions. We can save the file. And now we can start defining the analysis steps. Okay, so let me go and check a list of analysis steps. Okay, now you will find in this folder 3 examples. You will find it tomorrow. The basic one, where basically I create the entire model all at once, so the standard way, and I will show you what happens in this case. So when you do this, you can just start by defining the boundary conditions. And the first step can be add fixities. I go under model, analysis, not analysis, pattern, add pattern, and I want to add a constraint pattern. Now the constraint that we have, at least for the first stage of the analysis, we just need to impose the fixities. So we have 3 of them, we make room for 3, and we select fix in X, fix in Y, and fix in Z. Okay? So at this point of the analysis, we apply the fixities. That's why I said before, here we define the condition, but it is here that we decide when to apply them, okay? So at this point of the analysis, only the fixities have been used. No equal DOF, no boundary Coulomb, no less Coulomb boundaries, no dynamic force, and so on. So the first thing is that we have this fixity. We don't need to put the equal DOF now because, as you have seen, the fixities are applied on all the phases. So they just cannot move relative to each other. So there is no need to apply the equal DOF now. We will apply it later on. So the fixities, now we can just start with a vertical analysis. Now in this case, we want to use a static analysis. Otherwise, if we use a dynamic analysis, the self-weight of the elements that are applied instantaneously will create some vibration. So you will need an extra analysis to dump them out. What happened? What does it mean? Do you have any problem? I mean, what is the problem? Okay. Hi everyone. Can you all hear me? Yeah, we had a connection problem. Unfortunately, these days, this connection is a mess. Sorry for the inconvenience. Okay, let me share my screen. Okay. Did you miss a lot? I think only the last few seconds. I'm here. So if someone can tell me, yeah, just 1 minute. Okay, thank you. So as I said, okay, let me go back. I think everyone has seen how to apply fixities. I will show them once again. So I use the constraint pattern, add constraint, and then I assign the three constraints, the fixities in X, Y, and Z. Okay. So as I said, at this point of the analysis, all we have are the three boundary conditions in terms of fixities. Then, as you've seen, we defined also the equal dot constraints, but there is no need to apply them now, the equal dot, because actually, since we fixed the phases in X and Y, they can already not move relative to each other. So we will add the equal dot later on. So for the moment, we have the fixity. Now we can do the first analysis, which is the gravity analysis. I call it analysis gravity. And I want to make it static. Static because the self-weight in OpenSees given in the elements is applied instantaneously. There is no way to assign it to a ramp. Now, this can actually cause a problem if you use a dynamic analysis here, even if the time step is very large, because then you need an extra analysis step just to dump out the possible vibration that will generate from those vertical analyses. So I typically use a static one. Now, in this case, since we have many constraints, I typically prefer to use the penalty method. And for this example, 1 to the power of 12 is a good value. Then in the example that I will show you now, we are using a parallel solver. If you don't want, you can just remember that for parallel solver, I will change the reverse, the number to the parallel one. But if you want to run the same analysis I will send you tomorrow, I will send you two versions, one for the parallel OpenSees MP and one for the sequential, okay? So if you don't have access to a parallel OpenSees MP, you can just use the sequential models, okay? But the only difference is actually few parameters in the analysis. So for doing a parallel analysis, I use the parallel reverse cutting McKee number. And for this system, I use the MUMPS, okay? Then here we use, since everything is linear, to speed up the analysis, I use a linear solver with the initial stiffness, and then I use the factor only once. So we speed up on the factorization of the stiffness matrix. Of course, when you're doing a nonlinear analysis, you have to change this one. Test combat is not important because we're using a linear algorithm. And then the static integrator load control is fine, and we just go in one step to the 100% of the analysis. So we apply basically the entire vertical load. Then we keep load constant and we reset the pseudo time step to 0. Okay. So this is fine. First analysis, gravity. Then the second stage will be to create a recorder because we don't want to record the first stage. So we create the recorder just after the gravity analysis. Recorder. Then we go under recorders and PCO recorder. We choose a name, and this one is the model 3D basic. We want to see displacement, acceleration, velocity, and we want reaction forces, probably reaction force. Yes. We want to print it every time, and we want to see in these elements the stresses. Now, since this is typically to visualize the stress in a solid element, you can select the material dot stress keywords here. But unfortunately, the single point constraint does not follow the same rules followed by any other solid element in OpenSea. So they do not accept the material keyword. This is because they just have one integration point, so they decided not to use this keyword. But in this case, there is no problem. You can go under custom element results, and you can create as many results as you want. And in this case, I will just write stress. If you want also the strain, there's no problem. You go here and you write strain. Okay. Perfect. So this is our recorder. So next step is to, before doing the entire dynamic analysis, we want to add some Rayleigh damping. Let me call this damp. And we go under this command, Rayleigh. Oops, not region. Rayleigh. And we are going to use, let me see the values, I have them here. We have it here on the material parameters, 0.049. Yeah, 0.05. Let me approximate it. 0.05 and 0.000315. 315. Okay, so we have the Rayleigh damping assigned to the entire structure. Then the next step would be to remove the fixities. So as I said, we have the fixity boundary condition applied here. Then we do the gravity analysis. Then we remove, before doing the dynamic analysis, we remove the fixities. And we can call it remove fix. As we added, as a pattern, we have the add pattern. We also have a remove pattern. Now in this case, it was a single point constraint, so I choose remove SP constraints. And here I have to select all the single point constraints that I want to remove now. And now we have fix X. Actually, we have three of them, fix Y and fix Z. Okay, so this command will basically remove the three conditions that we applied instead here, the first step. Okay, so by now we don't have any more the fixity boundary condition. And of course, now the model will be unconstrained, and we need to replace those fixities with equivalent forces. And that's why we can use now the force from reaction condition that we defined here. This is a load, so we can add force from reaction. Since it is a load, we add it as any other load, so we go under pattern, add pattern, load pattern. And we don't want, of course, we don't want to add it incrementally. It will be constant. So it will be applied all at once. So as soon as we remove the fixities, we apply the same forces, the same reactions as forces, and they should not change during the analysis. That's why before we created the time series constant. Okay, so we choose the constant, and here in load, we create room for one, and we use the force from reaction.
Can you check the damping if it's correct?
Yeah. Let me check the damping. Probably I made it wrong. Let's see. Is it correct?
Oh,
yeah. Yes. Okay. Sorry. Well, now here we have also the forces from reaction. So we remove the fixities. We add them back as equivalent forces. And the next step is to add. Actually, in this first model, I will create the entire model at once. So the Leismer-Kuhlemeyer elements here will be available since from the beginning of the analysis. Even if it is not strictly correct, in this kind of analysis, it is fine, because since the first analysis is static, so the dashpots will not work. But even if it was dynamic, those two phases were fixed, so there was no relative displacement between them, and of course the dashpots were not going to work. So we can safely add them from the very beginning. Later on, I will show you how to add pieces of model one by one. Now we have the force from reaction. Now we have to apply the boundary conditions at the bottom, which is, of course, the Leismer-Kuhlemeyer condition, and the equal dot for the free column, for the free field columns, because now we removed the fixities in X and Y. We add them back as forces, but we need to constrain them in an equal dot fashion so that they will be periodic. So once again, I need to add some conditions. In this case, add Leismer-Kuhlemeyer at bottom and free field equal dots. So I go here under pattern, add pattern, and this time it is a constraint pattern. And we have just multi-point constraints. So 1, for the Lesch-Meyer condition at the bottom, and another one for the equal dov in the free fields, and press OK. So just two multi-point constraint. So at this point, we removed the fixities, we added forces from reaction, and we added the absorbing boundaries at the bottom and the equal dov for the free fields. Now the next step is just to apply the horizontal forces at the base and then run the analysis. So another step, add dynamic force, pattern, add pattern, load pattern. Now in this case we choose the time series that we had. Now remember that this time series is actually now a velocity, and it is a velocity that will give us corresponding to this acceleration. And now we have to convert it into an equivalent surface traction. So we just let me put it as a note here. We want to put it as we want to convert it as a surface traction that will give us a peak acceleration of 0.g. Okay, so we need to take the 0.g and then we need to multiply it by material density times the shear velocity of the soil here. And this one will give us, well, I have the calculation here in the material parameters, which is this one, but this one is the maximum load multiplier, because the load was just unit force. That's why I decided to make the load a unit force. So that then I can use this multiplier. It's 7534.08. 7534.08. Okay. So this is multiplier for the load, and then we have the dynamic force here. And now we can just run the transient analysis. So I will copy paste the gravity analysis and then I will change it. So gravity analysis, add it, and let's call it analysis transient. Now in this case, we'll just define it. So we convert it to transient. The penalty method is the same, parallel, maps, linear solver as usual. No, the test command is not important. We go with Newmark, 0.5, 0.25. But then here we choose 0 increments and a 0 time step. And we don't need to put the load constant. Why? When you're doing a parallel analysis, if I choose the number of increment here, it will print something from the test command at every step, at every increment. This is fine, but when you're doing it in parallel, it will print it for every processor, and it will be very annoying. One point. Second point is when you're using a linear algorithm like this instead, it will not print anything because the linear algorithm doesn't need any test command. So you will be there waiting without knowing the percentage of the analysis. So I decided to do something different, and this is something that you can do. This is not mandatory, but you can do it. So I will show you also how to use a custom STKO script to customize the way you can run the analysis. So here I just use 0 increments and 0 time step. So I just needed to define my analysis. Then I press OK. And then to customize the way I step through the steps, I can use a custom command. I call it run. I go in this command, custom command, which is basically a STKO script. I go here and I can open the STKO script editor. And in the file that you will have tomorrow, there is this file called custom run. So you can open it with a text editor and you can copy paste the contents here. Okay, so let me just give you an example. This one works for the parallel. As you can see, we have a variable here which is called process ID. Only if the process ID variable is 0, it will print something, and it will print the current increment, the number of iteration, which is, in this case, since it is linear, it will be 0, the norm of the error, which will be 0, and then the percentage of the analysis. The only thing that you have to set up at the beginning is the total time of the analysis and the number of increments. Okay. This one works for the parallel. In the sequential example, it will be exactly the same, but without this if statement, because of course you don't have the variable process ID. Anyway, this is a way to customize the analysis. So instead of doing analyze 2000 times, I say for increment which goes from 1 to the number of increments, do one analysis, and then print some statistics here, okay, to understand what is the percentage of the analysis. As I said, this is not mandatory, but it is a way to customize it. So here we have everything. Now the last step that we need, we already created a mesh. Now we need to create it once again because we changed the model along the way. So let me mesh it. We have a question here. Should we turn on the load constant for the reaction force? Yes. Well, actually, for the reaction force is already constant here. So you don't need to, we need just to keep the load constant in the gravity analysis, which actually is not important because the gravity load is already constant by definition of the element. It doesn't follow a time series. I just need to check the load constant because then I want to reset the time step to 0, not because I really need the load constant. And then after apply the load const, the force from reaction, I don't need to put any load const because the force from reaction is using a constant time series, so it will be constant anyway. Okay. Okay, so once again, oh, I think we have one more question. Okay. And in any case, we don't need to put it because then this is the last step of the analysis. So in any case, we don't need to put load constant here. So now I created the mesh, as you have seen. If you want to run the parallel analysis, you need one extra step. You need to partition your model. Now, in my case, in this computer, I have 8 processors. So I can go here, partition. I can choose the number of processors that I want, in my case 8. I can do a partition. Then I can see if it is fine for me. It will see, okay, in each partition I have more or less this number of elements, this number of nodes, this number of elements. I can check all the partitions. If it is fine, I click done. Okay. Keep in mind that every time I remesh it, so if I watch the partition now, it is fine. Every time I remesh it, because let's say I made a change in the mesh, the partition will be lost, so you need to recreate it. Okay. And in this case, I put 8 once again. Done. Now keep in mind that when I create the TCOL file now, it will create a TCOL file for OpenSees MP with exactly 8 processors. So if you run it through STKO because you have your own OpenSees MP version, this is fine because STKO will automatically call the OpenSees MP command, passing 8 as parameters to the MPI executable. But let's say you don't have OpenSees MP on your computer and you want to run it, for example, through the Design Safe web portal, as we explained in our first webinar. Pay attention to run the OpenSees MP with the same number of processors as the number of partitions that you're using in the example, okay? Otherwise, you will have strange errors. So now, of course, you can run the analysis. This one with 8 processors will take about 10 minutes. Now I will not run it. Now I will show you directly the results. This one is the model basic. So is this one. Okay. Now, basically, when you run the analysis in parallel, you obtain an output with the name that you gave to the process, to the recorder, with a postfix here, which is part 0, part 1, until part n, which is basically is the number of processor, but 0 based, so from 0 to 7. If I click in one of them, it is not important, it will load all the others that share the same name convention, okay? So I click on the first one, and it will load all the 8 files, as you can see here. Now this one is the basic model. Let me show you. Now by default, when you open a model, STKO will create a new plot group with a default plot, which is the deformed shape. This is not the most exciting plot, but it is a plot that can be by default shown. Now in this case, I want to show instead a surface color map. Okay, now this is our surface color map. I want to go on stage 2, it is fine. I want to show acceleration, of course. Now let me go back to the beginning of the analysis. Yeah, by default, the deformation vector is the first results that you have in alphabetic order. Now, since in alphabetic order acceleration comes before, I usually change it to displacement. Otherwise, you will see strange deformations. So if you want to see the deformation, always choose displacement. Instead, we use acceleration as the color map, okay, to visualize here. Now, for the acceleration, the maximum acceleration that you expect is 3.4 more or less. So I can put a maximum here so we can see the waves and how they propagate here.
So make it red.
Yeah, of course, as you can see, now let me show you just something. This is at the beginning of the analysis, we don't have any acceleration, then we keep on going and you will see the acceleration. But before doing this, let me show you, of course, by default, you have some predefined color maps, the rainbow one or the hot one. But when I see waves propagating, I personally prefer to use a custom one that you can easily create, which is red-blue, a typical color map that they use in electromagnetic fields. And you can put a blue to one end, red up to the other, and white in the middle. That basically nicely show you the waves with this white line in the middle. And then, of course, you can simulate your model. You can run your video to see what's going on. Let's see. Then, of course, if your model is too large, like this one, and let's say your computer is not good enough to visualize a very large model, you can always restrict your model to something. For example, let's say I want to visualize only half of it because it is symmetric. So I can go and select it like this. And then I say, okay, I want to visualize only half of my model. So I select this one and click show. And this will show me only this half. Let's say I don't want to visualize the zero length elements because I really don't want them. So I can just select them and click hide. Okay, so you just see the solids here. Or even you don't really want to visualize either the free fields because they are actually boundary condition. You don't need them. You are focused on the soil, so you can select all of them, and you can hide them as well. Okay, so you just have this half of your model, and you can see what's going on. It will be easier for you to run it. Okay, so as you will see the wave propagating from the bottom. Why I fixed it to the top value? Because in this case, it will be easier to visualize when the wave will be reflected and when they will go almost to zero. Of course, keep in mind that the Leismer-Kuhlemeyer boundary will absorb these outgoing waves, but not perfectly, because if the incident angle is not exactly aligned with the Leismer-Kuhlemeyer condition, something will be reflected, but it's the best approximation that we have now in OpenSees. Okay, so let's keep it going a little bit. As you can see, the waves are going down. They're going to be absorbed. There will be a slight reflection here because we are modeling a bedrock, so we expect some reflection from the bottom. Okay, now let me show you something. Then when you will run the analysis, you will see the rest of the analysis, and then you will see that all the waves are going away. Let me show you the deformation, for example, because I want to introduce you to the next step. In this case, we have done a vertical analysis and then the horizontal analysis. Now let's say, okay, I want to visualize also the displacement field because I want to see how this, I want to increment the displacement deformation because I want to see how this soil profile is deforming. But then you will see that even if you increase this value, the vertical deformation is so high that basically hides the horizontal one. And probably you don't want to see this. You can solve this problem, but actually this one is only a visualization problem, and then you will need this feature also later on by using the initial state analysis. If you use the initial state analysis, you can run the gravity load, then you turn off the initial state analysis, and you will see the same model with the same stress state, but with a zero displacement. So this is nice to filter out the initial displacement from the output, but this is just a visualization point of view. But then, since you're doing soil structure interaction, in the next webinar, we will see how to add a structure here in a second stage. And when you're adding something in another stage, it is better to do it in the undeformed shape. Otherwise, it will be a mess to link something that was actually here, but then it will be applied when the soil is already displaced. It will be a mess depending on the element that you use. So it is better to use the initial state analysis. For the initial state analysis, you have all the documentation in OpenSees. It is here, okay? And as you can see, however, the initial state analysis is pretty easy. You just need to create an initial state analysis wrapper as a material. Like in this case, for example, you create your own material, then you create an initial state analysis wrapper material, and you assign this one to the element. And then, instead of running just your analysis, you first turn the analysis, the initial analysis on, then you do your analysis, and then you turn it off. When you turn it off, you will see that your model has zero displacement, but then it has a state of stress equal to the one obtained at the end of this analysis, okay? Of course, however, there is a problem. The first one is a minor problem, that this command will remove all the recorders. So if you define the MPCO recorder before the analysis stage, you can move it down after the analysis of command. There is another problem here. They say that this command is tricky to use in dynamic analysis because this imposing the displacement to zero will create some undesirable vibration in the next steps of the dynamic analysis, and we will see this one. So I will first show you how to use this staged analysis. We will see this kind of vibration, and I will show you how to get rid of them. So let me go back to our model. We can save it, and now we can save it as with a different name, with model 3D init stage. And this one will be actually it's already prepared, so you will find it here under model 3D, this one, init stage, and the associated output. This one will show you the initial state analysis, but with the drawback of having this undesirable vibration. And then we will fix it. So how do you turn the initial analysis on and off? So the first thing that you want to do actually is to, as you've seen, we have created the entire model all at once, okay? Now we want to do something different. In the first stage of the analysis, as I told you before, we don't need the Lesmer-Kuhlemeyer between the soil and the columns, okay? So we can add them later on. So we actually want this model at the very first stage to be only the soil and the vertical fields, so they will be subjected to their vertical load. Then in a second stage, we turn off the initial analysis, and we apply the Lesmer-Kuhlemeyer conditions, okay? So the first thing that we need to do for this is to create another material, which is called material soil, but this time it will be the initial state wrapper. Initial state wrapper is actually very easy to define. You go in material, ND, wrapper material for initial state analysis, initial state analysis wrapper. This is very easy. You just need to select the material that you want to convert into an initial state material and the number of dimensions. In this case, we are in 3D, okay? So you press OK. It is this one. Now, for the sake of clarity, I move it up here. Now you can go in property. As you can see, all of them are assigned this soil material. So you can click select to get back the selection. And then I drag and drop the initial state wrapper. So now they will not have the plain soil material, but they will have this one, which wraps the initial material to make it compatible with the initial state analysis, okay? So this is the very first step. The next step is to create an initial analysis. Those basically are two custom commands, because in STKO we don't have the initial analysis command, but it is very easy because we can create a custom command, and we can call it initial on. Then we go in this command, custom command, and we use article script. And as you've seen here, the initial analysis command is very easy. Here there is an example. You just need to call initial state analysis on, so you can copy paste it. Okay. Then I take this one and I move it just before the gravity analysis. Okay. So before running the gravity analysis, I turn on the initial state analysis. Now let me clone this one. I rename it initial state analysis off. And I do a small change here To turn off the initial state analysis, you just replace on with off. Press OK, and now you have to move this one just after the gravity analysis, like this. So the first note that we found here, it was saying, warning that the initial state analysis off will remove our previously defined recorders. Here it is not a problem because the recorder is already defined after the gravity analysis, okay? But let's say it was defined before, you can just take it and move it after the initial analysis off command, okay? So this one is enough for creating the initial analysis. Now we want to do a couple of changes. Now this one will turn on analysis on and off, but I want to show you how to add a piece of model, pieces of the model stage by stage. So we said the first thing that we want to do is to add the soil and the free fields, and then we want to assign the Lesmer-Kuhlemeyer condition at the sites. So how do we do this? We have a special command in STKO which is called, let me call this model soil and free field. We have a special command that is not mandatory, but I will show you where it is. This command, model subset. The model subset allows you to create, to tell STKO not to write the entire model at once at the beginning of the analysis, but to write pieces of model explicitly when you tell it to do it, okay? But actually, before doing this, you need selection sets. So let me go back to the selection set here. I need to create a selection set containing the pieces of model that I want to create at every stage. So the first stage, I want a new time step, a new selection set, and I want to select only geometries. So I can select all of them. As you have seen, I switched off the selection of interactions, so I do not select interactions. Right click, and then I use a name called set geo. Okay, this is for the entire geometry. Then I need another selection set for the parts that I want to assign to create in a second stage, which in this case are the Lesmer-Kuhlemeyer condition between soil and free fields. So I create another set. In this case, I really want to select only interactions. So I go here and I select this one, which are the interaction for the Lesmer-Kuhlemeyer between soil and side free fields, and these ones, there are instead Lesmer-Kuhlemeyer condition between lateral free fields and corner free fields. So right click and I give it another name. Let's say set Lesmer-Kuhlemeyer, and I press OK. Now that we have these two sets, we can go back here and say, okay, now the first part of the model that I want to add, let's call it model geometry, or in this model I call model soil. Okay, in the example I called it soil. You go under model, miscellaneous command, model subset. And here you can include all the selection set that you want in this stage. Now in this case we have just one called geometry. So in this case, as you can see from the modeling, if you apply just one of these commands, then you need to specify explicitly when to add all the other parts. If you do not define any model subset command, as we have done before, the entire model will be written as one as the default behavior. And in this case, instead, we want to explicitly define the stage analysis. So the first stage will be to add the model soil. Now, of course, this will be created at the end, and we need to move it at the very beginning. So before adding the fixities. So we create the soil, then we can apply the fixities, because the fixities are applied on nodes of the soil. But if this model is not present, the fixity will not be there. Then we need another model subset. So I can clone it, and I can call it model Lesmer-Kuhlemeyer sides, and I change the subset to the set of the Lesmer-Kuhlemeyer. So at the second stage of the analysis, this Lesmer-Kuhlemeyer will be added, and I will do it just before, let's say, before adding the Lesmer-Kuhlemeyer at the bottoms. Anyway, just before the dynamic analysis. So it is not important here, but it should be between the initial analysis off and the transient analysis, okay? Actually, when we do when we create the model piece by piece, it is important to understand the position of the damping. Because now if you apply the damping here, it will be applied only on the first model. So we can, just to make sure, we can move the damp command just before the transient analysis. Because when the damping command, the really damping command is issued, it will apply the damping coefficients to all the elements that have been created previously to this command. Okay, so just to make sure, just place it before the transient analysis. Now basically this is all done, so we can save it. We didn't change anything to the mesh, so the mesh is still there. We can run the analysis. And what you will obtain is instead this other result. Let me close this one, and I will open the Model 3D initial stage. Okay, so once again, the default plot, which is the deformed shape, I don't want it. I want the surface color map. Okay, I want to go at the very beginning of the analysis. Okay, now here you can already see some problems. Now first, let me move from deformation acceleration to deformation displacement. But as you can see, we have many peaks of acceleration at these points. This is exactly what the author were telling us here in the third warning. When we use initial state analysis wrapper, you will see undesired vibrations in the next dynamic step. So this is actually a problem. How can we solve this one? Now let me show you what's going on here. I just want to highlight a piece of this geometry. Show, okay. I will show you that we obtain what we want apart from this kind of side effect. So let me switch off mesh edges. I want to change it to this one. Okay, and I want to increase the displacement field to 5,000. Now, as you can see at the very beginning of the analysis, if I look at the displacement, okay, the displacement is almost zero. Okay, here we have some values which is very small, but it is almost zero because this one is actually the first stage, the first step of the second stage. So there is already a small vibration here. But the displacement is almost zero. But however, we have the stresses. So the objective of the final aim of the initial state analysis is fine. So we have a state of stress with a zero displacement, and this is what we want. The problem is that we have a side effect. We have this undesired vibration. Let me put the magnitude. And actually, we need to solve it, but this is a problem because as we keep on going in the analysis, this vibration has a quite important value until they disappear and the rest of the analysis starts. But probably this kind of error can be very large. You don't know beforehand how large it will be. So how can you solve it? You can either create a dynamic analysis between the static one and this one, hoping that you can dump out all those vibrations. The problem is that how do you decide how long that analysis should last to dump out everything? Actually, I think that this problem instead is a pure implementation problem because we have found out that just create, instead of doing a dynamic analysis, you can just create another gravity and another static analysis just after the initial state analysis off. So you can do something like this, clone. You can put this one just after the initial state analysis off without any load. So you just need a static analysis. So it is not important. You put 1, 1. You don't need, you need actually to put the load constant to 0, not because of the load, but because you want to reset the time step to 0. Now, this static analysis, it is sufficient to save the displacement at this time that will be used as the initial state in the dynamic analysis. And with this simple trick, you will remove all those vibrations, okay? This one will be the initial state. Let me save it as a name. The initial state analysis, let's call it fixed. This kind of fix was not mentioned here, probably because they thought it was a physical problem, but actually I think it is only an implementation problem because with just a simple static analysis like this, without doing anything, the subsequent analysis will be fine, and you will see it here. So as you can see here at the beginning, we have quite large accelerations. Then I close this one and I open the output from the third file, which is the Model 3D initial stage relax. I called it relax because I was trying to do a relaxation analysis, but it was not necessary actually. Okay, and I convert it to surface color map. As I did before, I want to select only the relevant part of my model. Okay, show. And I want to select the displacement at the displacement field. The acceleration is fine. And I want to go at the very beginning. So now as you can see at the beginning, we have extremely small, we don't have any spurious vibration here. We just start with the Richter wavelet at the base, okay? So this simple trick allows you to use the initial state analysis without any drawback. So you just need, keep in mind that you have to do an extra static analysis just after the analysis is off. So you can just see now the effect of the initial state. We can put, oh, let me do something different. I want to visualize it using the volume plot. So for people doing solid modeling, probably the volume plot is kind of more interesting. Let me show you how it works. But basically, it's like the surface color map, but it will render also the inside using transparency map. So you will see what's going on inside the model. Okay. And to have a nice plot, you can switch off the mesh edges, so you can see only the feature edges and the volumes inside. Then you can choose your favorite color map. In this case, for me, is the red-blue here. Use the acceleration, and then I use the displacement and deformation, and I put 5,000 just to exaggerate the deformation vector. And I want to use a maximum value of the acceleration to 3.4. It was the maximum acceleration expected there. And now you can run the analysis, you can run the simulation here. Now let's see what's going on. And I will show you how to work with, as you can see, the volume plot allows you to visualize what's going on inside. And now, as you can see, we can finally visualize the output, the displacement deformation, only relative to the dynamic analysis. So you don't have the extra deformation that covers everything, basically, which is the vertical deformation. And now, of course, you can play with, when you're doing volume plots, you can play with the transparency map. 0 is mapped to the minimum value and means completely transparent. White means completely visible. Then inside it is interpolated. Now, let's say we want to make it even sharper, this division between visible and not visible. So we can create another point here and we can make it black. Okay, so if you want to increase the non-visible part, we can just drag it through the white like this. In the same way, we can create another white here and we can bring it like this. Okay, so you can play basically with those values and you can look what's going on inside. Okay, so let me do a first, let me go back to the interesting part of the analysis. Okay, then we will look at the animation. At the end, the volume plot is something nice to visualize what is actually going on inside your volume. Okay, so you can see the wave propagating through the top. Then this imperfection in the soil profile will create some reflections. And then little by little, you will see how they get absorbed by the side boundaries and by the bottom boundaries. Okay, so okay, now this one can go on. Then when you will have your own model, you can see all the steps of this analysis. Now the next step would be to create a superstructure here, but it almost took 2 hours. So probably we'll postpone the modeling of a superstructure and the nonlinear analysis with contact elements and nonlinear soil materials to the next soil structure interaction webinar. Okay, so this one, let's say, was more focused on modeling and these advanced boundary conditions that are already available in OpenSees, but are very difficult to implement when you do the tickle file by hand. Instead, with a user interface like STKO, you can automate these kind of things, and it is much easier. Okay. So if anyone has questions, I think we have finished for today. So thank you for being in this webinar. And if you have any question, yes, so we have one question there. Oh, thank you. Just a question. I have a question here. You said those are zero length elements defined between nodes of soil elements, but they're finite length, don't they? Are they actually two node link elements? No, they are not two node link elements. They are zero length elements. And in fact, when you will run the analysis, you will see that they give a warning. But actually, that is not a problem because the zero length does not take into account the length, the physical length. So I just made them distant just because it was easier for me to select the various pieces, the different pieces. If you want, you can move those pieces together, and the zero length will have an actually zero length. Instead, if I used the two-node link, it would have created some problem because the two-node link takes into account the distance, okay? Because it couples displacement and rotation. So don't use two-node links in these cases. Always use a zero length. Then, if you want to use a finite distance or not, it is not a problem because it doesn't change anything in the analysis. It just gives you a silly warning saying warning the zero length as a finite length instead of a zero length, but it is not a problem. So this is another question. I see. Usually I couldn't be able to run OpenSees with zero length. Maybe it was my mistake. Probably it just when you use zero length elements with a finite length, the only problem is that it gives a warning, but that warning is not an error. Then I have another question here. May I have a question out of the context? Okay, just let me answer to this question and then proceed with this question here. Why don't you define a stiffer material for the free field elements? Yes, I told it in the beginning of this webinar. When I was doing the 2D examples, I was following some of the examples I found online, and they always talked about giving us an increased thickness in the 2D case. But actually, I was running this 2D example, and I started with defining different materials with of course, I cannot use an increased thickness because this is a 3D, so I was using an increased stiffness. But actually, I've seen that nothing changed. So I prefer to keep just the standard stiffness of the soil material. It was not changing anything. So probably because I made the free field columns already 10 units wide. So it is already 10 times, let's say, stiffer than the other elements, but I actually see no difference. Then I tried to increase the stiffness of the material in the free fields by 10,000 times, but nothing changed. So the solution was already correct in this case. But actually, I have to investigate it because I couldn't find any reference about this increased thickness in 2D or increased stiffness in 3D in the literature. They don't talk about it. So I need to study it a little bit better. But for the moment, I couldn't find any difference. So let me go back to this question. Yes, please. Okay, probably you cannot see this. There was a question by someone, Sardash. Yeah, you can give a question. Is it possible to use modified Ibarra and Kravinkler model for the rotational spring with zero length elements? Yeah, of course. The only difference that when I define the zero length in this example, I simply said it should be 3D with just 3 degrees of freedom. Now, in this case, you should say 3D with UR, so displacement and rotation, and then you assign the modified Ibarra and Kravinkler Medina model for the rotational degree of freedom. But of course, you can, I mean, a zero length is just a collection of uniaxial materials. Then if you place this material in the direct component, translational component, or in the rotational component, it's just a matter of what you want to represent. But a zero length material is just a collection of at most 6 materials for the 6 degrees of freedom of the spring. Okay. And actually, we have done this example exactly with the modified Ibarra in our previous webinar on lump plasticity reinforced concrete models. So you can go back and look at our previous webinar. It will be there. We are actually using modified paragraph intermediate in a model. So the UA, the soil material is non linear. We still use elastic material for the free soil color. Actually, I didn't see any reference on this, but I think we should use the same nonlinear model. I'm pretty sure about this, but probably in the next webinar, since I want to do the same analysis, but with nonlinear materials and a superstructure, we can investigate on this topic. But yes, I'm pretty sure it should be the same one. Okay, so is there any other questions or? Yeah, of course. The very next webinar will be on the out-of-plane modeling of material failure in masonry. But then we will do another soil structure interaction problem with these topics here. So